Okay, this is section 1.2, and we want to look at elementary row operations. So we're going to use these in solving equations, linear equation systems. So, we've already solved some linear systems, but now we want to kind of make this a little more formal, a little more algorithmic. And so we have three types of elementary row operations. One is just interchanging rows. So this kind of makes sense that if I interchange rows, then the equations that are represented by a given matrix don't change. So let's take something very simple here. Suppose I have x plus y equals 5 and 2x minus y equals 2, something like that. Then my augmented matrix for this thing would be 1, 1, 5, and 2, negative 1, 2. Now, if I call this my row 1 and row 2, and I write a new system here where I swap row 1 and row 2, and so swap row, well, let's use a little bit different notation than that. The book uses the double arrow, but let's go row 2 goes to row 1 and row 1 goes to row 2 in this new one. That's 2, negative 1, 2, 1, 1, 5. But now the interpretation of that is that this augmented system here is just this 2x minus y equals 2 and x plus y equals 5. And hopefully it's pretty obvious in this case that, yeah, interchanging rows, all we did was we swapped which one of these two equations we wrote first. Well, who cares, right? Write either one first, it doesn't matter. And so swapping a couple of rows of the matrix that represents this system doesn't do anything to the solution of the system. So interchanging rows gives me the same solution as I had to begin with. Okay, so there's interchanging rows. Then the second thing is multiplying a row by a non-zero scalar. So, multiplying a row by a non-zero scalar. Because certainly if I multiply a whole row by zeros, really what that's done is gotten rid of one of the equations. Well, I would expect a new answer if that happened, if I got rid of an equation. But again, so we have x plus y equals 5 and 2x minus y equals 2. And so we have our 1, 1, 5, 2, negative 1, 2. And so there's row 1, row 2. Now, if I take 3 times row 1 and put that into row 1 and leave row 2 the same, that's 3, 3, and 15, and 2, negative 1, 2. And again, right, this is just representing 3x plus 3y equals 15. and 2x minus y equals 2. And again, hopefully, we remember our algebra well enough that we've been doing that for years, right? Multiplying both sides of, say, this equation by 3 keeps the same solution. We've been doing that sort of thing for a long time. Now, can you prove it? Well, yeah, we aren't going to worry about that proof, but it can be proved. And at this point, though, in our life, we just kind of take it as fact that we can do that with real numbers and the equations involving real numbers. So, yeah, that's our second thing. We can multiply a row by a non-zero scalar. And then finally, third, we can add a multiple of one row to another. And that is a elementary row operation. And again, that if we have our 1, 1, 5, oops, well, let me start with our x plus y equals 5 and our 2x minus y equals 2. Then we have our system 1, 1, 5 and 2x, oops, 2 minus 1 and 2 for our augmented system, row 1, row 2. And now if I take, suppose I leave row 1 the same, but I take negative 2 times row 2, row 1, try that again, negative 2 times row 1 plus row 2, and I put that into row 2. So I have 1, 1, 5, and so I take negative 2 times 1, that's negative 2, add that to 2, I get a 0. Negative 2 times the 1 up here, that's another negative 2, add that to the negative 1, I get negative 3. And then I get a negative 10 plus 2, that's a negative 8. And we have that, which is the system x plus y equals 5 and negative 3y equals negative 8. And this system should have the same solution as that system. So that's our third one. Now, again, why does that make sense? Well, we can do that because, and we mentioned this, I think, in a previous video when from section 1 when we were just solving equations. All we've really done is added negative, whoops, did I do that right? Negative 10. We've added negative 10 to both sides of the second equation, right? So if you want to think about it that way, right, we had x plus y equals 5. We had 2x minus y equals 2. And then what we did was we simply rewrote the first equation, but we added 10, or actually subtracted 10 from both sides of the second equation. So we had 2x minus y minus 10 equals 2 minus 10. Okay, and again, we know that we can do that and not change our solution set. And so, that's fine. But what else is equal to 10? Right? Well, from this first equation, I know that 2x plus 2y is equal to 10. So I can just do a substitution, and I have x plus y equals 5, and I have 2x minus y minus 2x plus 2y, like that, equals, and 2 minus 10 is negative 8. And then I can rewrite that again, x plus y equals 5, and distribute the negative and collect things up, right? And I have a 2 and a negative 2, so there's 0x. And I have a negative y and a minus 2y, so there's negative 3y equals negative 8. So that's the idea back here of adding a multiple. So I can add a multiple of one row to another, which I did here. And all you're really doing, because these things, are equations, I can do this kind of substitution. So really, when I add that multiple of another row, I'm just adding a constant to both sides of one of the equations, and we know we can do that, and we get our answer. Okay, it's just a little more efficient and certainly a little more general to talk about it instead of as a constant, to talk about it as a multiple of one of the rows. Okay, so that's our three row operations, and then of course the theorem, and then row equivalence. They've got the definition, row equivalence. And so row equivalence, one matrix, some matrix A is row equivalent to another matrix B, to matrix B, if B is obtained by a sequence of row operations. Okay, so a sequence of row operations B is on A, or from A, so we start with A, we do a bunch of row operations, we get B, then B is row equivalent, and our theorem, somewhere is the theorem. That's a good question. I'm looking at the text right now. And somewhere, it might not be till 1.3 is the, I'm not noticing, at least I don't see that they, yeah, I don't see the theorem. Well, that's interesting. It's kind of weird. So let me toss that in. The theorem is that if an augmented matrix B is obtained, I don't have to go through the obtained, is row equivalent, okay, to an augmented matrix A, then the systems represented have the same solution. Okay, so that's the key here, right? Is that if we do these elementary row operations and start with some augmented matrix A and end up with an augmented matrix B that's maybe in reduced row echelon form where we can read the answer off very easily, what we know is the two share the same solution. I said have the same. I didn't say same what? Same solution. Sorry about that. Same solution. And so that is how we are going to attack solving systems of linear equations. So there we go.